Section 2.1 and 2.2, we're now on to page 4. So example 5 asks us to, the graph of the function g is given. We're asked to sketch the graph of the derivative. Lots going on here, so let's look at the function g, which is given. Hopefully you can see this blue line, which I'm tracing, which is the given function, which I've tried to draw that same shape over here. Now what we learned is first thing we want to do is find all of the horizontal tangent lines, because that is where the slope of the tangent line is 0, which means the graph of the tangent line will have a 0 height. So following this first mountain shape, we see that right here is a horizontal tangent line. So we're going to go directly to the x-axis and draw the first point of our derivative function. And then I'm going to continue to the next, in this case valley, where I have a horizontal tangent line, and I'm going to go directly up to the x-axis where I enter the second point of my derivative function. And I continue this process where sometimes I'm having to head down and other times I'm having to head up to get the key y heights of 0 of my derivative function. Now the next thing I want to do is find wherever the graph is decreasing or essentially increasing, because if the graph is decreasing, then the derivative will be below the x-axis, whereas if the graph is increasing, the derivative's graph will be above the x-axis. So as I look to the left of the point I've drawn, my graph is headed all the way uphill until I get to that first horizontal tangent line. That means all of these tangent lines that I'm drawing have positive slopes. My graph is increasing. So when I want to draw to the left of this point, I want my derivative to be above the x-axis, which this orange line is. Now, true, it could be curved, it could be very flat, it could be very steep, but really all we're looking for is to the left of this, that your curve, in my case, the orange piece, is above the x-axis. In between my next two horizontal tangent lines, a y height of y and the next y height of y, my graph dropped in between those two regions. That means all of the graph should be below the x-axis. I chose to make it kind of a shallow connection piece, but so long as it's connecting those 2 points below. Then I'm headed uphill until I hit the next horizontal tangent line, so the rest of the graph is above the x-axis. Downhill to the next horizontal tangent line. So this region going downhill means that this shape of my graph, in this case I chose to draw a lower shaped U, it doesn't really matter. It won't be a hard V, but it could be a close to feeling V shape, right? And then I'm increasing forever, so therefore this graph is above the x-axis forever. And you can see the graph of the function that was given and my interpretation of the derivative based on that function. And one last piece about that. Let's talk about being differentiable, right? We have found out limits don't always exist, even though the function may or may not exist at a point. So we need to talk about the derivative of a function at some specific value. We'll just say a to be generic, and if or when it does exist. So what we'll focus on is f is differentiable at some point a, meaning you can take a derivative. And if that's so, that also means it's continuous at the point A, and we'll talk more about that in other sections, but let's look at the contrapositive. If our function is not continuous, then it is not differentiable. Most noticeable in this middle graph, right? When I'm graphing, I have to physically lift my pen off the page and drop it down to continue drawing the graph. This is that jump discontinuity that we've talked about, but that also means whatever this value A is, there is no derivative at A, because as we try to find the slope of a tangent line as H is super close, whether it's to the left or the right, we're getting completely different slopes between these two values, so it's not going to happen. Turns out to be the same if you have a corner or a cusp, a sharp point. Think about it. Which tangent line would you draw? It's kind of like trying to balance a pen on the tip of a pencil. There's too many options, so there is no derivative. And lastly, don't forget, if you ever have a vertical tangent line that looks like this, the slope of that line does not exist. There is no slope. It's an undefined slope, so therefore the derivative is undefined.